Good afternoon, students. I hope you are well. So, today is lesson 7 for our chemistry class. I hope you have studied our previous lessons. Okay, so in this lesson, of course, it is chapter 6 from page 188. But let me just review a few things with you from the previous lesson. I hope you have studied it because it is very important. So before we took the ionic bonding, we started, of course, section 3, ionic bonding and ionic compounds. Okay, and we took what is an ionic compound. It's compound of positive and negative ions that are combined so that the numbers of positive and negative charges are equal. Okay, so it's important. Please review it very well. Okay, and also we took the characteristics of ionic bonding. We took what is a crystal lattice. Okay, what is it? We took all of that in the previous lesson, so please study it very well. So now we will start with an example, another example in page 188. Okay, before we took examples, and now this is one extra. This is the crystal structure of NaCl. You see here, this is example. The figure shows the ions that most closely surround a chlorine atom, a chloride anion, and a sodium cation within the crystal structure of NaCl. So you see here, like this. Okay, so the sodium, you see, the sodium surrounds the chlorine. The sodium, of course, cation, surrounds the chlorine. Okay. So now let's continue. Now, the three-dimensional arrangements of ions and the strengths of attraction between them vary with the sizes and charges of the ions. So of course, when you have another compound, different charges, for example, if you have Ca2 plus and other compounds like, for example, CaF2, it's different. The crystal is different. So now the arrangement of ions and the strengths of attraction also it's different. It could be higher or it could be lower. It depends on the compound. Okay, and also what else? Okay, and the numbers of ions of different charges. All of this varies. Now, for example, another one in calcium fluoride. You see here there are 2 anions for each cation. Each calcium cation is surrounded by 8 fluoride anions. At the same time, each fluoride ion is surrounded by 4 calcium cations. You see here? So this is the crystal structure of CaF2. Okay? This one here, the positive ion, okay, cation, the calcium, Ca2 plus, and you can see here this, the fluoride. Okay? This is the fluoride. So let's continue now. Now, to compare bond strengths in ionic compounds, okay, chemists compare the amounts of energy released when separated ions in a gas come together to form a crystalline solid. Okay, so I want to know the bond strength in ionic compounds. So how strong is this bond in this ionic compound? Is it stronger than, for example, in another bond in another ionic compound? How do I know which one is stronger? The chemists or scientists, they measure what? The amount of energy, you see, released. Okay, when these ions, these separated ions in a gas, of course, this is in a gas, come together, they bond together to form this crystalline solid that we have seen before. So this is called what? Lattice energy. This is called what? Lattice energy. Is the energy released when 1 mole of an ionic crystalline compound is formed from gaseous ions. Of course, lattice energy values for a few common ionic compounds are shown. Okay, in figure 3.6, you can find it in the book. It's not important, no need to memorize it. This is just example. Okay, now the negative energy values indicate that energy is released when the crystals are formed. So you'll see a negative, okay, near the number. This means the energy is released, okay, not the value is negative. So let's continue now. Now, the main idea from this slide is what? Differences in attraction strength give ionic and molecular compounds different properties. Okay, so these differences, Okay, so now each ionic compound has different properties. That's obvious. Okay, so for example, let's read together. The force that holds ions together in ionic compounds is a very strong overall attraction between positive and negative charges. So in a molecular compound, the covalent bonds of the atoms making up each molecule are also strong. But the forces of attraction between molecules are much weaker than the forces among formula units in ionic bonding. This difference in the strength of attraction between the basic units of molecular and ionic compounds give rise to different properties in the two types of compounds. Okay, so let's continue now. So in this slide, what can we see? Okay, we see there are factors depends on the strength of attraction between each each individual molecules. So these factors are what? The melting point, boiling point, and hardness of a compound. All of this depends on, you see, how strongly its basic units are attracted to each other. So for example, now do you see? Because the forces of attraction between individual molecules are not very strong. So when these attraction forces are not strong, so what will happen? Many molecular compounds, what you can see, the melting point will be low. You see, the boiling point will be low. The hardness, no, it will be a soft compound or brittle. You can break it easily. Now, in fact, molecular compounds are already completely gaseous at room temperature. So please highlight this. So many molecular compounds, but of course there are exceptions, but many of them are already completely gaseous at room temperature. In contrast, the ions in ionic compounds are held together by strong attractive forces in higher compounds. So obviously, okay, so ionic compounds generally have what? Now, as we said before, so stronger bonds. So this means higher melting point, higher boiling point, stronger. These compounds are stronger. It's harder to break them. Okay. Now, of course, they are stronger than the molecular compounds. Now, what else? You can see ionic compounds are hard but brittle. You see why? In an ionic crystal, even a slight shift of one row of ions relative to another causes a large buildup of repulsive forces. So you will see there will be repulsive forces between these ions. Okay, those forces make it difficult for one layer to move relative to another, causing ionic compounds to be hard. Okay, so remember this, it's important. So let's continue. Now, in the solid state, so we are speaking now about ionic compounds. In the solid state, the ions cannot move. So the compounds are not electrical conductors. So what should I do to make this compound conduct electricity easy? The answer is easy. We melt it. So you see, in the molten state, we melt this compound. So in the molten state, ionic compounds are electrical conductors because the ions can move freely to carry electrical current. So many ionic compounds can dissolve in water. Okay, so when you dissolve it, the solutions, they conduct electricity. Okay, so let's continue now. So this is example. You see figure 3.7. You see the attraction between positive and negative ions in a crystalline ionic compound causes layers of ions to resist motion. This is what in the solid state. Now, when struck with sufficient force, the layers shift so that ions of the same charge approach each other, causing repulsion. Okay, so this is example. Okay, now this is the end of our lesson. Thank you.